Welcome to this video on a non-parametric Bayesian approach towards online sequence learning, based on the paper by Dias, Bruno, and D'Souza. In this video, we will explore how to build a machine learning system that can predict the next observation in a streaming sequence, while continuously updating its knowledge as new data arrives. Here is what we will cover. First, we will define the online sequence learning problem and understand why it is challenging. Then we will see why the Bayesian framework is the right tool for the job. We will then look at how observations are encoded into sparse binary vectors using a codec structure. After that, we build up the hidden Markov model formulation and the grid-based Bayesian filter. Finally, we walk through the full algorithm step by step and see it applied to anomaly detection. Let us get started. Online sequence learning appears in many real-world applications. Think about stock market forecasting, where prices arrive as a continuous stream, or network intrusion detection, where packets arrive in real time, or industrial sensor monitoring in factories, where machines generate continuous measurements. In all these cases, the system must predict what comes next based on what it has seen so far. Here we see a time series, a sequence of observations arriving one by one, shown as blue dots. After observing some data, the question is, what will the next value be? But there is a deeper challenge. The process generating this data is non-stationary. As shown by the red portion of the signal, the distribution of the data shifts over time. The model cannot simply be trained once and deployed, it must adapt continuously. This leads to two tasks that must happen simultaneously. First, continuously learn a model of the underlying process. Second, use that model to predict the next observation, all in real time, with no retraining. Why is the Bayesian approach the right tool for this problem? Classical machine learning requires collecting all training data upfront, optimizing model parameters in batch, and then deploying a static model. When the world changes, you must retrain from scratch. This is slow, expensive, and fundamentally incompatible with streaming data. The Bayesian approach works differently. It starts with a prior belief, what we think is likely, before seeing any data. Then, as each observation arrives, it updates that belief to produce a posterior. No batch retraining is needed. One observation equals one update. Watch what happens here. The blue curve is our prior belief about some parameter theta. When observation 1 arrives, shown by the yellow arrow, we compute the posterior, shown in green. The distribution shifts toward the new evidence and becomes narrower, reflecting increased certainty. When observation 2 arrives, the process repeats. The posterior gets even sharper. This is captured by Bayes' rule. The posterior is proportional to the likelihood times the prior. Each new observation refines our belief incrementally, which is exactly what we need for online learning. A key challenge with Bayesian inference is computational tractability. Performing exact inference over a continuous, high-dimensional observation space is generally intractable. The solution proposed in this paper is a codec, a structure that encodes continuous observations into a sparse binary space, where exact Bayesian computation becomes feasible. Here is the pipeline. An observation yn in the continuous space omega y is passed through the encoder my to z, which maps it to a sparse binary vector zn in the space omega z. A decoder mz to y maps it back when needed. The binary space omega z consists of vectors in the set of 0-1 sequences of length dz. The key property is sparsity. Only a few bits are active at a time. In this example, only 3 out of 20 bits are active, so the L1 norm is 3, much less than dz. Why does sparsity matter? Because close observations in the continuous space map to similar, sparse codes in the binary space. This means the codec preserves the geometric structure of the original data while enabling efficient discrete computation. The encoding function assigns each observation to the nearest cluster center in the partition of omega y, a form of vector quantization adapted for Bayesian inference. To model the sequence, we use a hidden Markov model, or HMM. The intuition is simple. The world has hidden states that we cannot observe directly. Think of weather. Whether it is sunny or cloudy is hidden, and what we observe is temperature. The HMM has 3 layers. At the top are the hidden states Sn, shown in blue. These evolve over time according to transition probabilities, the probability of moving from state Sn to state Sn plus 1. In the middle are the encoded observations Zn in green. Each hidden state emits an encoded observation according to the emission probability P of Zn given Sn. At the bottom are the decoded observations Yn in orange. These are obtained by applying the decoder Mz to Y to the encoded observations. The yellow box highlights the current time step N, where we are at this moment. The Markov property is the key assumption that makes this tractable. The observation Zn depends only on the current state Sn, not the entire history. Similarly, Sn plus 1 depends only on Sn, not past states. This conditional independent structure allows the Bayesian filter to compute exact posterior probabilities recursively, one step at a time. The grid-based Bayesian filter is the heart of the system. Its goal is to recursively compute the belief about the hidden state, the probability distribution P of Sn given all observations up to time n. Step 1. We represent this belief as a probability vector pi n given n-1. Each element of this vector is the probability of the hidden state being in a particular category. The bar chart shows this distribution. Each bar is one hidden state's probability. Step 2 is the prediction update. We apply the transition matrix F to the current belief to produce a predicted belief for the next time step. The equation is pi n plus 1 given n, proportional to F times pi n given n-1. F encodes the state transition probabilities. Watch the bars change to green as the prediction step shifts probability mass according to the transition model. Step 3 is the measurement update. When a new observation arrives, we incorporate it using the observation matrix H. The equation is pi bar n plus 1, proportional to H times pi n plus 1 given n. H encodes the observation likelihoods. The orange bars show the updated belief, now sharpened around the most likely state. The full recursive update equation is shown at the bottom. It combines transition probabilities, observation likelihoods, and the previous belief in a single sum over all hidden states. A key question is, how do we represent uncertainty about the probability distribution itself? This is where the Dirichlet distribution comes in. The Dirichlet distribution is a distribution over probability distributions. If we have C categories, a Dirichlet distributed random variable is itself a valid probability vector of length C. Its hyperparameter alpha is a vector of positive pseudo-counts, one for each category. On the left, we see the three-dimensional simplex, the space of all valid probability vectors for three categories. Each point in the triangle is a valid distribution over three categories. With alpha equal to 0.5 for each component, samples cluster near the corners. Extreme distributions. With alpha equal to 1, samples are uniform across the simplex. With alpha equal to 4 for the first component, samples concentrate near pi 1. With alpha equal to 3 for all components, samples cluster near the center, balanced distributions. On the right, we see how alpha updates as observations arrive. The rule is simple. When category K is observed, alpha K increases by 1. This is Bayesian updating. For categorical data, each observation adds a pseudo-count to the corresponding category. As more observations accumulate, the distribution concentrates around the true frequencies. The equation at the bottom says, the predicted state distribution is drawn from a Dirichlet with hyperparameters alpha, updated by the current belief and observation. Now we are ready to put it all together in algorithm 1. The non-parametric grid-based filter, or NPGBF, running for one time step n. At each time step, the algorithm does three things. It updates its belief about the hidden state. It predicts the next observation. And it stores everything in memory M for the next step. The algorithm takes as input the current encoded observation Zn, the current belief Bn given n-1, and the memory M which stores learned associations. Step 1. Retrieve the pseudo-counts alpha from memory, indexed by the current observation and belief. This is a lookup, no computation needed. Step 2. Sample the predicted state distribution pi from a Dirichlet with those pseudo-counts. This gives us a full probability distribution over hidden states. Step 3. Encode the predicted distribution into a sparse binary belief vector using the Bell function. This compressed belief is what gets stored and used as the next memory key. Step 4. Retrieve the observation pseudo-counts alpha bar from memory, indexed by the new belief. Step 5. Sample the predicted observation distribution pi bar from a Dirichlet with those counts. Step 6. Predict the next observation as the symbol with highest probability. The confidence in this prediction, pi bar of k hat, tells us how surprised the model would be if the actual observation is different, enabling anomaly detection. The memory M stores associations from observation belief pairs to pseudo-counts, enabling one-shot learning. Each new pair is remembered immediately. Let us now watch the algorithm run on a concrete example. We use 8 hidden states, 10 observation symbols, and 3 active bits in the belief. At each time step, we will watch all 6 steps of the algorithm execute in real time. Time step 1. The observation is category 3. The pseudo-counts alpha are initialized near 0 and update as we observe data. We sample a state distribution from Dirichlet, encode it as a sparse belief with 3 active bits, retrieve observation pseudo-counts, sample an observation distribution, and predict the most likely next symbol. Time step 2. Category 3 is observed again. Notice how the pseudo-counts for state 3 have increased. The model is remembering that this category occurs frequently. The belief becomes slightly more concentrated. The prediction confidence increases. Time step 3. Category 7 appears, a less frequent observation. The model adapts, updating the relevant pseudo-counts. The prediction still works, though confidence is lower for this novel observation. As we continue through more time steps, the model learns the patterns. Pseudo-counts grow where data is consistent. Predictions become more confident. Anomaly scores drop as the model understands the stream. The key insight from this example is that learning and prediction happen simultaneously. No separate training phase is needed. Every observation immediately improves the model. One of the elegant bonuses of the NPGBF framework is that anomaly detection comes for free. The intuition is this: when the model has high confidence in its prediction, meaning the probability assigned to the predicted symbol is close to 1, and the actual observation matches, everything is normal. But when the actual observation is something the model considers unlikely, that is an anomaly. The anomaly score is defined as 1 minus the probability assigned to the predicted symbol. A score near 0 means the model was confident and correct. A score near 1 means the model was very surprised. Here we see a time series signal with 3 anomalous points, shown in red. Below it is the anomaly score chart. The threshold is shown as the orange dashed line at 0.35. As the observations stream in, shown as the animation builds up, the anomaly score for normal points stays low and blue. When the 3 anomalous points arrive, marked with warning labels on the time series, the corresponding bars in the score chart spike above the threshold in red. The filter automatically detects these anomalies because its predicted distribution assigns very low probability to the observed symbol. Normal observations receive a score around 0.1. The model predicted correctly. Anomalous observations receive scores around 0.8. The model was genuinely surprised. No separate anomaly detector is needed. It emerges naturally from the prediction confidence. Let us recap what we have covered in this video. We started with the online sequence learning problem, predicting the next observation in a non-stationary stream without retraining from scratch. We saw why Bayesian inference is the right tool. 1 observation equals 1 belief update. No batch training needed. We introduced the codec, the encoder-decoder structure that maps continuous observations into sparse binary vectors, enabling exact Bayesian computation. We built the hidden Markov model formulation, showing how hidden states generate encoded observations through transition and emission probabilities. We derived the grid-based Bayesian filter with its 2-step recursive update. Predict using the transition matrix F, then update using the observation matrix H. We saw how the Dirichlet distribution tracks uncertainty over categories, with pseudo-counts that update naturally as observations arrive. We walked through algorithm NPGBF step by step, 6 steps that retrieve, sample, encode, retrieve again, sample again, and predict. And we showed how anomaly detection emerges naturally from prediction confidence, with no additional machinery required. The 3 key contributions of this paper are a novel grid-based non-parametric filter, an efficient memory-based implementation using VGRAM nodes, and a unified framework for simultaneous prediction and anomaly detection. 1 observation at a time, no forgetting, no retraining. Thank you for watching.